after I pose the problem is I want to have a bit of a discussion to see how everybody else would solve it before I show you how I solved it. So, a little bit of background about me. This work I did, in 2000 to 2004, I was at a company I started called Colloquis. Colloquis was acquired by Microsoft last year. Then I moved over to a company called IMMI, which stands for Integrated Media Measurement Incorporated. And to understand what they do, think about Nielsen ratings, but modern. Instead of having to wire television sets and having panelists keep journals, we have a new method that uses state-of-the-art technology, and I'll show you how that works. Currently, I am doing a new startup called Boopsy Inc., and it involves software on cell phones, and we could talk about that later if you like. The work I did for IMMI was as a consultant. It was not my company. I wasn't the founder. But I was an early engineer and was given the title of architect. So we're talking about the data pump at IMMI. The company was founded by Tom Zito and Al Alcorn in 2004. I started at the beginning of 2005. Sorry? Oh, that's not us. We spent about a year doing the first version. And this involved finding out if the technology would work. We implemented it, and we had it up and running. But what we built was not scalable. We didn't know what we were doing that first version. We figured out, we learned a lot. And in 2006, we turned to doing V2, which would be scalable and a production system. We had a team of about 5 or 6 people during V1, and those people carried over to V2, but there was a lot of different things to do, and so the data pump component largely fell to me to implement. This talk is about that design and implementation. So what we do is we do data collection from essentially 3 different sources. We process that data, and out comes panelist viewing behavior. I'll explain a little bit more how that works in additional slides. But basically, we recruit panelists the way you'd imagine. They have to be demographically representative of the markets you're interested in, the ages you're interested in. You want people that are a mixture of high tech and low tech and so on. So it's a panelist recruitment process. Once you've picked the panelists, they've agreed to the terms, then we give them a free cell phone. Data comes in from the cell phone. We also collect reference audio. Basically, we record about 100 channels off the air in currently 6 markets. And the 100 channels include a lot of television channels, some radio channels. And then we have a third source, which includes a catalog of advertisements that might run on television and radio. As well, we get first-run movie audio into the system so that we can tell if the panelists go to the movies. The data gets collected. We do acoustic matching, so we can match what the phone heard with what we recorded off the air. And based on that, we know what you saw. The last step, this software, the acoustic matching, is pointwise. Every sample that comes up with the phone, from the phone, we can figure out this sample was there, this sample was there, this sample was there. Then we do a process called attribution. Well, if we see a sequence of samples that all match the same channel being viewed, then we can assume that they saw that channel for that period. So that's the process of creating coherent viewing data from a bunch of point samples, this last step. Well, then we go into reporting, but I consider the data pump part of the system to end with the attribution. All right, so I covered a lot of this. We give them a phone that is a singular 3125, runs Windows Mobile, and we have our software on that phone. It's a full-featured phone, so this isn't a compromise that somebody has to make if they're a panelist. They get a full-featured, nice phone, and it's free. And I don't know what the current policy is, but I believe panelists are being subsidized $50 a month as well towards their cell phone bill for participating. The panelists have to make this their primary cell phone. That means, keeping it powered up, keeping it with you all the time, but that's what people do with cell phones, so that's not a hardship. In other words, essentially what we have here, instead of you having to keep journals and having to punch in when you are starting to watch television, we have here a zero-footprint solution to measuring media consumption, because all we're doing is swapping one cell phone for another, but their behavior doesn't have to change outside of that. They do have to stay in compliance. So if panelists have this habit of leaving their cell phone on their side table when they go to sleep, and the television playing while they're asleep, these are issues that we might have to sort out. The end product, which is the result of the data pump that gets fed into reporting, is the panelists viewing information. And so you can see here that this panelist likes to channel surf an awful lot. And it seems to me that maybe they were busy doing laundry or something, because they keep coming and going. And here they seem to be looking for something to watch. And you get the idea what the data looks like. So at one end, we have a panelist with a cell phone. At the other end, we can reconstruct this data. And I'll remind you that, that this data can include television viewing, radio, and movies. So for example, if you go from your house to your car, it will pick up the radio, and then you get to the movies, you watch the movie, we capture all of that. That's why the company is named Integrated Media Measurement. What's the secret sauce in this company? What is it that we talk to the VCs and show them the new stuff that we can do? I figured out there are 4 pieces. There's the software on the cell phone. And believe me, cell phone programming is a lot harder than it seems. So you set out to do this, you get something that works fairly well, and now you're only beginning. Because if this needs to be running 24/7 without crashing the phone, and the phone needs to continue to behave like a phone, that itself is a real challenge. And there are a whole bunch of system issues. It turns out to be a very complex process. So the cell phone software is one of the secret ingredients. The media monitors, these are basically PCs with audio capture cards. And a single PC can grab 32 channels of audio. It does a fingerprint. It uploads it over, say, a DSL connection. And we run maybe 3 of those at once in a market. So that gives you 96 channels to record. Now, some of those might be hooked up to cable. And the analog cable channels, you can pull maybe 50 channels or 60 channels simultaneously off the analog cable. If you need to get premium channels, then you need a stack of set-top boxes. We also have antennas to pull the radio stations off the air, and there's a lot of tricks to wiring up those antennas. So the media monitors is a component that's very interesting. The acoustic matching technology is software that was created by a Stanford graduate who then created a company called Shazam. And Shazam is very well known in the industry. We did a straight license for the software. So we don't actually look inside, but we don't need to look inside. It does point sampling only. They created the software to solve the problem of what song am I listening to? So you basically take one point sample. They'll match it against an enormous database of songs, and will tell you what track you're listening to. But that's a point sample only, which takes us to the 4th secret, which is how do we do attribution? How do you take all those point samples and turn that into the television viewing data? And an issue there is that there's a lot of ambiguity that you have to resolve, and there's certain other kinds of things you have to deal with. Now, everything else is glue, and it's essentially an IT problem, moving data through the system, storing it in the database, and all that. So the ground rules that I have in being able to tell you about this is I can talk about anything that's patented, and I can talk about a lot of things, but I shouldn't be talking about anything that's trade secret. Well, I can talk something about each of these, but that's really not why I'm here to talk tonight. This is the MySQL meetup. So this thing that's basically an IT problem that you could basically hire IBM and pay them a few $1 million and they build it for you, my solution is actually interesting, and that's why I wanted to talk about it tonight. We can talk about these other things a bit if you have questions, but we'll leave that later. And as I say, some of it I can talk about, and some of it they consider trade secret. So the scale of the problem. In designing V2, we were told that we would need to have, say, 1,000 panelists in each of 6 markets. We need to have 100 reference channels per market. We'd like to keep the raw acoustic samples for more than 2 months, maybe 3 months. And by the way, once we do that acoustic matching, the Shazam technology, then we pretty much have no more need for the raw samples. But we find that there are reasons, as we're developing the system, to go back and reprocess. And that's why they want to keep it for a while, even though we could process it that one day and we most likely wouldn't need it again. They want the results available daily at 3 a.m. local time. Well, keep in mind that that reference audio and the samples from the phone come up at the earliest at midnight, local time, which means that we have at most 3 hours to get through the entire system and publish the data. How big is this as a database problem? And this is one of the first things I want to get some feedback. Is this a big database problem or not? If you guys have experience building big database problems. 200 samples per second, but so it's not like 200 hits per second on a website, because every single one of these is a write, is a database update. And it comes out to about half a billion samples per month. So I have one data point. I'd like to put some more in there if anybody has them. I know Facebook does 1 billion page views a day, which is essentially 2 orders of magnitude bigger, but that's a lot of reading and a lot less writing. So how does that compare? I don't know. But so my sense is this is a fairly big database problem. Any ideas? Not compared to, say, Google or Facebook, but no feedback on that. Okay, well, we'll come back to that. How much data is it? The media monitors send up samples that are about 5 minutes long at 100 kilobytes each. And if you do the math, we get 35 gigabytes per day, or about a terabyte a month. The panelists send up 4 kilobyte samples twice a minute, which comes out to about the same amount of data. That's just a coincidence that they happen to be about the same amount of data. The first thing we want to do then is partition by market. There's essentially no interaction that happens. So if we store all of the data separate by different markets, we find that each market grows by about 1/3 of a terabyte per month. So one of the principles I'll talk about, I wanted to design this to inexpensive hardware because we had the opportunity to do that. If you're designing the entire system, then you can take advantage of inexpensive hardware. If you can use middleware to a good advantage, then you might shorten the development cycle, but it may need some more robust hardware. But since we had to start and do everything at the low level, we might as well take advantage of inexpensive hardware. So one design point I looked at was, let's say I could take 500 gigabyte drives, which were available for about $300 at the time. And I could put 4 of them on an inexpensive motherboard because there were 4 SATA ports. And I'm running RAID 5, so that gives me 1.5 terabytes of data. And does that work for me? And it translates to give me about 3 or 4 months of storage, and that's exactly what the requirements call for. So it doesn't sound like there's much headroom there, but in fact, we don't always have 100 channels. We don't often have the 1,000 panelists, at least not yet. And the phone software does squelching. So if it's quiet, then it doesn't bother to send up any samples. And that saves us maybe about a third, say 10 or 15 gigabytes a day, a third of the phone traffic. On top of that, hard drives are bigger now. We could get terabyte drives if we wanted to. So we do have plenty of headroom. And I think this was a good design target. And so that's what I went for, was to build on this commodity inexpensive hardware. This is called the illities of database. You got all these. So scalability, as I said, we're going to partition the problem horizontally. That gives us better performance and better capacity. And since we aren't, it's not like eBay where everybody is going to be able to see all of the items for sale. There's no interaction like that. This is an easy one to partition. We can, just if we want, build completely separate systems however we want. And then we just have to aggregate data at the end. Data integrity. So we don't want to lose data. And how do you do that? The easy answer is we were thinking, we came to, let's just make 3 copies of the data. And we could talk about that a bunch more. That's where it gets interesting. And the cost, I've talked about the cost. I wanted to target that knee in the curve pricing. So if we can do that, we save a tremendous amount of money because products like EMC, right, they'll give you better performance, better availability and all that stuff. But for each, whatever linear factor better they are, they're an order of magnitude more expensive. So if you need that, it's worth it. But if you don't, you can save a tremendous amount of money. Maintainability, we kept an eye on that. I like to make the code as simple for the system administrators to deploy as possible. And we'll talk about that a little bit more. Now, what's really interesting about this problem is that availability is not a high priority item. This is not transaction processing. We're not selling books on the internet. So if things go down for a half an hour, that's totally fine. In fact, the phones and the media monitors, which are collecting the data, will store hours or days worth of data. So in fact, we could be down for a day and it wouldn't be an issue. I mean, the one question is, do we have enough computing power on the back end to catch up? But if we allow for the possibility of downtime, and then there's also that 3 a.m. in the morning issue, but if we allow for downtime, then again, things become much easier. We don't have to worry about it so much, makes the coding much easier, and the price comes down. All right, so here's some general rules of thumb. It was a very small team. This part of it I did largely myself, and I didn't want to work that hard. So keep it simple. Minimize the number of moving parts. In other words, if I could do this thing this way and this thing that way, that's 2 moving parts. If I could do both of these tasks with the same code, then I'm better off, even if it turns out to be unconventional. I like to use generic installations. So basically, stay as close to what you get with the Debian install as you can, minimizing what the administrators have to do. And for example, where that's going to play in is replication requires a lot of operator interaction, a lot of system administration before you can start using servers. And so one of the things I looked at was, is replication the right solution? We do as much as possible in the application and not in the system. So if the system administrator could be installing packages so that the application could run, it's much better if we design the application to not need those packages in the first place. So we, for example, were very strict on not allowing packages when possible. Things like date manipulation is totally gratuitous. That can easily be put into the application and save the administrator some trouble. And you say, well, okay, here's 10, 15, 20 packages you have to install and you're done. What's the big deal? But the big deal is that the application is evolving all the time, which means that it's more packages all the time that need to be added. And you have machines that are deployed with the 15 packages you needed, and now you need 4 more packages. And it just becomes a real difficult problem. So the only packages we rely on are things like DBI and a few others that are really big, important packages, maybe reading Excel spreadsheets. But when it comes to date manipulation, all those other things, we put that into the application. Automatic failover is very expensive, and we've talked about that in this forum before. People think it's easy, and in theory it's not so hard, but to get automatic failover to work right is hard. So given that we don't have the availability requirement, that we be available all the time, at the very least we start with a system that will trigger an alert and have operators intervene. But given that we do look for single points of failure, we design them out of the system. There are very few single points of failure, and those that are there, if there's a failure, they don't prevent the system from progressing. Maybe not on the entire problem, but maybe one market is offline and 5 out of 6 markets can proceed, and that way we don't have as big a problem in catching up once that market is restored. So with that in mind, we came to what's a pretty obvious architecture. We have media monitors around the country collecting data. We have phones around the country also collecting data. That data is all being sent to some spoolers. We currently use round-robin DNS for the devices to pick which spooler to talk to. And then the spoolers, the first thing the spoolers do is they take the data from the device, they write it to hard disk, and return, let the device go as quickly as possible. We don't want to tie up the devices any longer than we need to. Once the data is on the disk, we now try to write it to the storage servers. Now that becomes the interesting question. This last step was, what we ended up doing was innovative, and it's still very controversial within the company. What happens here? And this is where I'd like to have a little bit of a discussion if people have ideas. So we have data on the spoolers that need to be written out to the storage servers. The storage servers are market-oriented, so we need to take a look at each sample, decide what market it's in, and then somehow commit it to the storage servers. And given that we have 3 servers per market, how do we allocate those servers? How do we make use of them? Any ideas? This was the audience feedback part. So somebody should have some ideas.
So is the problem how quickly you can decide which region it's in? Or?
That turns out not to be an issue. In fact, there's a slide that talks about, well, why do we have 2 spoolers or more? And the answer is it's not for performance. One spooler is enough. We have more than one spooler only because of redundancy. So one spooler can easily handle this problem for the design requirements. So let's take a look. How do we store blobs? We have 100 kilobyte chunks. How are we going to store them on our storage servers? Ideas?
What kind of file system do you use?
That's a design parameter. So would you pick a different file system based on the requirements? It turns out that, well, remember we say that each of these servers can have about 1.5 terabytes based on that inexpensive configuration. And that's good for maybe 3 or 4 months worth of data.
And after that? And you want to keep it, or?
Well, that gets down to what happens when they fill up. Okay. How does the data get from there to there? From the spoolers to the storage servers. How do the spoolers know which samples go on which storage servers? So what would be a conventional solution? Let's start with, we have 3 servers in each market. How would you configure those so that they all get the data?
The 3 are redundant,
Right.
Yeah, that's 3 copies.
So how would you do that?
Were you just doing a post over to something and then?
So you're suggesting how do we go from the spoolers to the storage servers? Okay, so how do we?
Well, so firstly, I'd say you want your spooler to do some kind of lookup to decide where it's going to go.
Okay.
And as long as you don't have too many regions, that's pretty easy to do that fast.
Remember, 6 is the design requirement.
Okay, yeah. Just
Right.
keep it right in memory, and then you.
All right, so you say in memory over there. Okay, okay. So, for example, think about single points of failure. Let's say there's a server that keeps track of which panelists go to which markets and which markets go to which server. If that server were to crash, we'd have a single point of failure. So you're suggesting instead we take that whole database and push it to each of the spoolers.
Yeah.
Okay, and that's good. And we do essentially that. Now, we need the data to get onto all 3 servers. How do we do that in any given market?
Oh, in parallel, meaning it's replicated across all.
Okay, so you said replication. By that, do you mean MySQL replication?
I don't know. Not a big fan of that.
Ah, good man. Ideas? Because the conventional solution is MySQL replication.
Yeah.
You write to one place and it replicates. Maybe 2 slaves off the same master. That becomes very tedious, though, as a maintenance issue. If the master goes down, you need to worry about the slave. We're not talking about master-master here, which is an interesting solution, but that's good when you have 2 boxes. We'd like to have 3 because, well, if you're doing replication, and we've talked about this in this forum, if you do replication in a database, that is not the entire solution. You also have to do backups. And the canonical example is, what happens if somebody issues a delete command accidentally? That immediately gets propagated by the replication. Deletes go very quickly. You say delete a whole table. And all your data is gone. So you need to have not only replication, but also a backup. And now that's 2 moving parts. And I spent a lot of time in thinking about V2 and how I was going to implement this, and I thought about those moving parts. There's a third moving part, which is the metadata pretty clearly will go from the spoolers to the storage servers. The metadata would be what time does this sample represent? This was recorded off CBS in this market from this period of time to this period of time. So that's the metadata. And then the data is the actual acoustic sample. Clearly, the metadata is going to be moving across as, say, a MySQL request using the MySQL protocol stored in MySQL table. So that's one moving part, right? We just said the second moving part is if we're using replication, we somehow have to do backups. So, well, let's say replication is the second moving part, backups is the third moving part, and we still haven't talked about what we're going to do with the blobs, these 100 kilobyte chunks. Ideas? I'll tell you what we did in V1 is we used a file system. You asked about file systems, right? We stored them in a file system, and you do the typical thing of 2 or 3 digits at a time, and you create a directory hierarchy. And that works fine as long as it's locally attached storage. And as long as you don't need to make copies of it. Turned out that we found it practically impossible to make a second copy of that. And remember, our requirements would have 3 copies. Secondly, there's a lot of parameters to tune. What's your fan out, different file systems, like Riser, for example, doesn't benefit from having the hierarchy. On the other hand, having several million files in a directory makes LS pretty unusable. So there are trade-offs there. And the big issue was we needed to get the data. So in V1, the spoolers had the big storage connected directly to them, stored in a local file system. And this is part of why V1 didn't scale. So we need to figure out how to get that data across the network. And one answer we tried as sort of to patch up V1 was let's use NFS. So how many people have experience with NFS? Okay. It has problems, doesn't it? What happens if the NFS server goes away? And you write to it, right? Now your application hangs in a really bad way. Okay, so NFS is problematic. NFS is really, really slow.
You're just doing writes, you're not doing bidirectional.
That's right. That's right. Just writes.
So 100 kilobytes per blob?
Yeah, per blob. Okay, so the answer is, at least what we did, and it worked phenomenally well, is we stored the blobs in the database. Is anybody surprised by that? Because conventional wisdom says, don't store blobs in databases. Believe me, it works just fine. Now, here's the one thing that you have to watch out for. If you have metadata in a table, in a record, and the blob in the same record, and you have an index, so you need to pick some records out of that table. And the optimizer does its thing, and it decides it can use these indexes to resolve the query mostly. That goes fast. But if it needs to then, it ends up with 100,000 records that it needs to look at some actual columns in the table to finish the query. It has to pull not only the metadata, but it has to pull the entire data, all the blobs, off the disk just to get that one extra column that it needed. And even though it's only 100,000 records, which it would normally be able to resolve quickly, you've magnified the size of the data by 2-3 orders of magnitude or more. So what they say is if you're going to store blobs in a database, in MySQL, for example, don't store the blobs in with the metadata. Just simply have a reference. Exactly. And that's what we did. So we have a unique ID for each sample in the system, unique across phone samples and monitor samples. And we have a metadata record. It has a sample ID. We have a separate table called bits, which simply has 2 columns. It has the ID and the blob. And if I were really smart, I would have put a date in there as well. Because as it is, we can't purge the bits table without doing a join. So anyway, we don't do any deletes, and that's a separate issue which we can talk about as well. But we'll get to that later. Let's see. So why are there 2 more spoolers? I mentioned that. How do we store blobs? I talked about that. How does the data get from there to there? Well, notice, so we'll get on with the slides, but notice we've reduced the number of moving parts. We're using MySQL for everything, which was an important consideration. A lot less effort, less communications with the system administrators, and so on. How do the spoolers know which one? We are going to put the data out there on the spoolers. What happens when they fill up? We'll talk about that. Any ideas about filling up? We only need to keep 2 or 3 months. So do we just keep deleting as we put stuff on there? Because people will tell you that you don't want to be deleting from databases. It takes longer than adding. So if you can avoid deleting and come up with a better solution, it's a lot better. And you hear this even from the likes of eBay. They don't delete anything. What happens when it fills up? And then how do you recover from failures? All right, so we'll talk about that too. If you're doing replication, you need a DBA/system administrator. And doing master-master is very interesting. You can do a lot with that. If you have a failure and have to recover the data somehow, it's a lot of steps. And so we'll talk about these kinds of things. All right, the spoolers. A single spooler is plenty fast enough, turned out. Writing it to disk, letting the device go, the phone or the media monitor, and then coming in every 2 minutes and looking at all the samples that are on the disk and trying to despool them. One machine can easily handle that. It has to write the data across to the database servers. And all of that went plenty fast for the number of samples we have, which is a fairly large number of samples, I think. But a single server has no trouble with that. So we run 2 or 3 of them, and they're designed so that they can cooperate on these unique content IDs. With, you don't want duplicate content IDs because then they wouldn't be unique. So there's some code in there that deals with that. But otherwise, in fact, I think we're not even using round robin DNS. That slide's wrong. We're using a service called DNS Made Easy. Does anybody know that? It offers DNS. It costs $50 a year for up to 50 domain names. And one of the things you get with that is service monitoring and failover. So if it sees one of the spoolers go down, it just switches the DNS over to the other one. The devices, if they fail to write, they do another DNS request, get the other one, and it's pretty cool. Okay, so let's talk about panelist management data. And also we talked about this data that maps panelists to markets. So that's one of the elements of panelist management. Panelist management data is SEP, somebody else's problem. All right? It's a generic database problem that you can apply standard best practices to. In fact, for V2.5, they've decided to switch to Salesforce.com. So it really is an off-the-shelf kind of thing. Subsets of that data are needed for the despooler, for attribution, and also for reporting. And so here's the thing. What we do is we let them collect their data however they want. We don't want all of our different components in our system to have to rely on one of their servers, because that's their problem, and we don't want our availability model to be screwed up by a failure on their end. So instead, what we do very simply is we push snapshots of the database to all of the servers. So what we see here is we see 2 spoolers, and we also have all the database servers, which is cut off on the slide. So daily or hourly or whatever, we simply take a snapshot of their data and push it out to all the databases. The reason it goes out to all the databases is for 2 reasons. One, we break that availability issue, right? If their server crashes, none of our servers has to wait. And we also solve an availability issue internally, that single point of failure. If we just copied their databases to one of our servers, then that one server would have to be made highly available. But the nature of this data is that it changes slowly. So we can just update it periodically and not have to worry about designing single points of failure avoidance to get that data everywhere. We simply put it everywhere periodically. Let's say that mechanism fails. Okay, so we can't get data from panelist management refreshed out to our servers when it's supposed to happen today. For our particular application, there's not much consequence. It means, for example, that we can't provision new panelists for today. And that's okay. We wait till they fix it, and tomorrow those panelists become active. And that's a very minor hit. Again, it means that we have very little consideration to worry about that problem. It's just something, it's an issue that becomes a non-issue. Yeah, okay, we covered all that. Now, the mapping table, so we have this one set of data which takes, says these panelists are in these markets. Now we have a separate set of tables that says these markets are on these database servers. I just want to point out that that is not part of the panelist management database. That's part of our operations. So there's a second table called map, and both of those have to be pushed out everywhere. So the question is, how do we push it out everywhere? We have, say, 6 markets times 3 servers each. That's 18 plus a couple of spoolers. So there's at least 20 servers right there. How do we get this table out to the 20 servers? Ideas?
We're using MySQL.
Let's say we are. That's fine.
You just do an artist kind of thing, and then.
Okay. Now, if you remember back to some of our rules of thumb, right? We wanted to do things at the application level when we could, and that's clearly a system level thing, right? The application programmer can't deal with it unless the application's running it as root, and you can't treat, in that case, you can't treat the database simply as a black box anymore. You have to know about file structure and everything. So I don't love that solution. It would work. You just push the MyISAM table out. You have to also worry about quiescing the table first, so when you copy, you get a good snapshot. So I don't like that solution much.
How much data do you have?
It's a good question. So it's very tiny. We have thousands of panelists times, hundreds of bytes. It's trivial. Let's say a megabyte. It's only a megabyte, right? Now, again, these people like conventional wisdom. I bumped into a lot of them. They say, well, you use replication for that, which is an enormous administration problem. And notice that the replication is different for this data than it is for the other data. So you end up having to have a very complicated scheme, and I don't know if you can do it with MySQL. But replication is not the answer either. And so I thought about this a lot, decided that a new solution was needed. And I've talked about this a little bit before in this forum. I wrote a program called Mirror. And this is basically the web page I copy and pasted. What you do with Mirror, oh, I like that usage, it says $0. I got to fix that. Can you tell what language it's written in? All you do is you say mirror, and then you can say a destination table equals a source table. So you can say mirror server1 dot this db dot this table equals, and if you like, you can say server2 dot star dot star. Actually, you do it the other way. So there's a star dot star mapping as well. So you can say server1 dot star equals server2 dot this table dot this database dot this table, and it will copy that table to the same location on the other server. It'll just straight up do a copy.
Is that your own? Is that an open source?
It is open source. It's my own code. I wrote it for this project, and it turned out to be exceptionally useful in a lot of interesting places. Now, it's better than that, because you can use wildcards. So you can say mirror space server2 dot star equals server1 dot this database dot star, and copy the entire contents of the database over. And it has a bunch of really interesting properties too. For example, you can put a -where flag in, and it will then apply that to the records it selects. So it only copy a subset, where some date field is more recent than a certain date. So you only copy newer stuff. So for example, we have actually a table that has television guide type data in it, which goes on forever, right? Ever since we started, we have data going back several years. But we don't need that in our production system. So when we propagate that data out, we do a where, and we might take the last 2 weeks of data. And it just propagates that much out.
The where is going to apply to all the tables in the database?
If you put a star in. Oh, the where. Yeah, see, so where and star don't necessarily interact properly. You may not want to use where with star. Another feature is -t, which actually looks to see if the table has been updated. If the source table is newer than the destination table, then it does the copy. Otherwise, it doesn't.
And where is it keeping track of?
There's a show table status something or other, which gives the date. Now, it may only work for my ISAM. And I don't have any guarantees that this will work with anything other than my ISAM. In fact, I think it's hardwired to turn InnoDB tables, all other tables, into my ISAM tables when it copies them. Then, since then, I've learned from listening to Jeremy and others that there's a lot of good reasons for InnoDB, and I may move that way. But we didn't see any benefits to InnoDB for this particular project. In fact, had I known about one of the features for my ISAM, which is this thing called concurrent commits or concurrent writes or something, I would have designed that in, because that's perfect for this thing. Since our data from the despooler out to the servers is write only, it would have sped things up tremendously. Okay, other features here. So the -t will only copy a table if the table is newer than the target. -do will run a command. Now, if you use -t with -do, then it will only run that command if it copied a table. So what's cool about this is you can create a cron job that says, copy any tables that I need from that server to this server, and if any of them change, run this command. And that came out to be really handy. You can turn on the compression flags, so you end up compressing over the network. And so generally, it's really handy. I think I have some demos here, some examples. The wildcarding you can see in the second example is really nice. You can copy it into other named things if you prefer. There's an example of -t and -do. I use -f for backing up. What that does is that creates a flat file that has the schema at the top. It has actually the show create table information, so you can use it to create a table. And then it just has a TSV file after that. Unfortunately, I haven't implemented the reverse yet, so I can't actually load a table from that, but that would be obvious. All right.
question. Do you use just plain selects or select into out files?
Plain selects or select?
Into out file, no data in.
Oh, no, no, plain selects. So that's an interesting question, is what does it really do internally? And the answer is it does things in a way that are as efficient as MySQL dump, for example. And everybody uses MySQL dump and these big, long pipes and things to do the same kind of thing, but don't have a lot of the extra features. All I do is I create a temporary temporary database on the target server. Target servers. Here's the best part: is I can read this table from the source and write it simultaneously to 15 different servers if I want, because there's a notion of grouping as well. I can create a group of servers, and it will do its best. It won't do it exactly, but it will almost get all of those tables updated simultaneously, because what it does is it creates a temporary database on the target server. It writes the table in there simultaneously. So you only ever have to read the source once. And so it reads the source and writes it out to a bunch of them, just sequentially, one after the other. So that's not tremendously efficient, but it's certainly better than reading and then writing it there, and then reading it again and writing it to the next one. Okay. And then what it does when it's finished writing all the data across all of the different database servers is it uses atomic rename. If you do rename this table to that table, comma, this table to that table, we can move the original table on the target database out of the way and move the new table on the target database into that spot atomically.
So there's a failure.
So there's no window where the table is missing, right? The database is operating on the old information, the old panelist information, let's say. And so just for example, I have data coming up from phones, and we have a new panelist with a new phone, and we have data coming up from that phone, and we don't have market data, mapping the IMMI of the phone into what market he's in. So we have to pretty much ignore that, and we just throw those samples away until that data shows up, until that metadata shows up. Well, my despooler is running and using the yesterday's version of the table, and when I do this update with the mirror program, that table gets swapped out atomically. So the despooler has no opportunity to see that table missing. So it works really well. Another thing that it does, we talked about this issue where you can accidentally type delete, and replication will propagate that all the way down the line, and everything disappears instantly. Well, I use this as poor man's delete. It's for smaller table, or poor man's replicate. I'm sorry. For smaller tables, it's not worth setting up replication. I just create a cron job that every minute or every 10 minutes copies the whole database over somewhere else onto my backup server. And for a lot of applications, that's totally fine. That can be done at the application instead of at the system level. And what's great is there's an option, I don't remember what it is, it's a new option, that says keep 10 copies of that old database. So if you have a database that's changing slowly, then each time the database gets changed because of the -t flag, it will copy it over to the new table, but it will leave 10 versions of the old table behind. So if you delete something and you don't realize it for a while, and that gets propagated, you still have 9 more versions where it isn't deleted. Yes?
So when you say you do it atomically,
yes.
Spooler cannot realize that we need to make the rename, and you need to rename twice, right? Then put the one to maybe to a 10 table or something, and then the one that you just copy there to.
So the question is.
Yeah. So you basically
right.
have to rename there.
But that's what's cool about the atomic rename that's built into MySQL. It's not 2 renames. The syntax is rename A to B, comma, C to D. Okay, so I can rename the live table out of the way and rename the new table to the live spot in a single SQL statement. So if I had to do it as 2 renames, then there would be a window in between where somebody would see that table missing. But I can do it atomically because the rename takes multiple renames in one statement. Okay?
Sorry.
That's fine.
One more question.
Sure.
When your mirror doing all this kind of magic, do you need to provide any username password to the database?
It's a good question. Mirror doesn't currently, I think Mirror currently has the username and password hardwired at the top. And something could be done, so there's a configuration file for it where you could factor that out. That's a good question. I mentioned that there are several good reasons why we want to copy the data out to the servers. One is it removes a availability issue. Another is, well, and so then you mentioned, I think you mentioned that you want to just keep it in RAM. Well, this is pretty much as good as keeping it in RAM. You have a local MySQL instance on each spooler where the data is, and it can get it from there. Now, the advantage, the reason we copy it to all of the storage servers, for example, where we have all of the metadata for the samples and all of the blobs for the samples, we copy it to all of them, and that way we can do a join of the metadata with the Panelist data on any one of those servers. So we go to market 3, Miami, and we need to pick out the samples for a given Panelist. We can, the metadata is in the same MySQL instance, so we can actually do a join. And that's another reason for broadcasting it across everything. It works really well. In fact, our runtime, when our Perl code starts up to do a report or to do processing or whatever, it doesn't even know what market it's in. There's some code that sets up the environment for the script to run. And one of the things it does is it interacts with DBI, and it creates the connection to the database. And which database? Well, you don't care. It picks the right one. So depending, if the people doing the report say, I want to report on this Panelist, it can automatically connect to the right database. And that includes, then it has an access to all the metadata, including the Panelist management data. And the people writing reports don't even have to worry, don't even have to know about this architecture. Worked out really well. OK. So we've talked about MySQL for everything. Let's see. Yeah, OK. It's surprising that nobody here seems to have a problem with MySQL for everything. In fact, as I say, I was a consultant at the company, and I built V2. And the company is now busy building V3 and undoing all of these innovations. They're going with vertical scaling. They're putting in EMC boxes. They are using replication. They are doing all these things that we had good reasons in V1 not to do. And so it'll be interesting. They're still relying on V2, hoping to replace it with V3 soon.
What sort of servers does V2 use?
It's cheap commodity servers. Actually, there's a real issue there, which is I built V2 on my credit card at Fry's. Right? So I needed half a dozen servers or whatever, so I am putting the hard drives in there myself, and it's a lot of fun to do that. And there are certain things I had to find my way through, such as how do you configure MySQL on RAID 5 and have it not suck? And there are a lot of hidden pitfalls, and there's a slide on that we'll get to later. So we have these generic servers. I picked Athlon XP 3800 Plus, which is the inexpensive dual-core desktop processor. And the database servers just ran beautifully. Okay, but we also do this acoustic processing, the Shazam technology, which is an intense floating point computation. And my servers melted. They just up and died. And we don't know exactly why, because I got busy on other things and nobody actually did the right postmortem, but they just went out and bought more expensive servers. And 60% of them up and died. So they went out and bought more expensive servers, and 30% of them up and died. So now they're running Blade servers, and they don't have any results yet on that. The solution occurred to us much too late. Why don't we just back off the algorithm and have it run slower? We need more servers, but that would have solved the problem, and I would have done that. So it was generic hardware, and now it's very expensive HP blades at $5,000 a server with no hard disk even. But it's cool because they can just build one image and have it propagate across all the blades and all the things that are cool about blades. Let's see. So MySQL for everything solved a lot of problems. It keeps it simple and because of fewer moving parts. Only one network protocol is needed. We know we had to have the MySQL network protocol already. We were worried about how do we get the blobs across the network. And the answer is, let's use the one we already have to have. And I can tell you today that it works great. Blobs are not a problem. in databases, and this has been rock solid. We understand MySQL. That's another reason. People keep saying, well, what about this, this open source project that does distributed file systems and all that? And because of its design, it should solve this problem better. And that may very well be, but we don't know anything about it. And there's just no reason to take that kind of a risk in an environment like this when we know MySQL pretty well. The concurrent update feature I mentioned would have, one of the complaints we have is that the despooler is feeding data in to the storage servers. And we have acoustic processing on the other side that wants to get the data out, and there's some locking going on. And I'll explain later why we're getting locking. And the concurrent update would have sped things up substantially, because we could actually make use of multiple processes writing at once and not worry about locking. You can actually have simultaneously bunches of writes going on at the same time with MySQL and MyISAM, if you don't ever delete. And we don't delete. But I didn't know about it at the time. I talked about the unique ID a little bit. It's amazing how people can manage to screw something up no matter how much care you put in. You want to make sure that a unique ID is unique. And so there's code that checks 6 different ways. And we still had problems. So another solution is just to have unique ranges for the different despoolers. But that can still get screwed up. So,
IDs
yeah.
for the blobs?
Sorry?
Those are
IDs for the blobs, exactly. We need to have a reference. So, here's what I've been hinting at all along. Is we do application level replication. Right? We don't use MySQL replication. And one of the points I make up here is MySQL replication is fast and application level replication is slower, but MySQL goes a lot faster if you turn off the bin logs. So we pick up some of the ground we lose by not using replication. And furthermore, it's fast enough, except it's not, and I'll explain why later. Replication is fast. It works with transactions, for example, nicely, so they can get unrolled if the transaction doesn't commit. We didn't particularly care about that for this application. Replication can't be controlled by the application. So if you have a server that fails, the application can't address that problem, right? The system administrator can address that problem. You could have the system fail over, but that's not the application that's doing the failover. That's the system administrator doing the failover somehow. Replication is fragile. It takes work. If you do the wrong thing, it breaks, and now you need to intervene. You must recover in order. So, for example, if we have a database server that goes down, we bring it back up. Well, you need to let it replay the logs to get back up to speed before you can start adding new data. We don't have that constraint. We can start putting new data in there and fill that hole later and simultaneously. So it's a lot less of an operations. There's a lot less pieces that have to be done in the right order. It makes it a lot simpler. Slips of the finger like that delete that we talked about. You blow away your entire table. With application level replication, if you're in there doing maintenance and you do that, well, you just blow it away on one. And I mentioned because of that, you need to do backups. Now, in our case, because of application level replication, that third copy, we could just think of that as the backup. And you might say, well, what about disaster recovery, putting it off-site? And these are things we could talk about. We haven't had that as a requirement yet. But, and maybe we should do backups, or maybe we can have an actual MySQL replication that takes us off-site, off of one of those 3 or something. But it gives us a lot of flexibility with fewer moving parts and at the application level, so it can be dealt with by engineering and not have to be a burden on operations. So let's see, yeah, controlled by, it's really robust because it's so simple. All you're doing is updating databases. As I say down at the bottom, the despooler simply writes the same data to 3 MySQL servers. If any one of those writes fails, it simply doesn't despool that sample. And the next time the despooler runs, it'll try that sample again. Now, you might ask, didn't we create some blob entries in the bits table and maybe even some metadata on 2 of the 3 servers, but it didn't succeed? That's okay, because the next time we come through, that same data gets a new content ID and works fine. Okay. One complaint that they did have of the original implementation was if any one, let's say one of the servers goes down, one of the storage servers. Okay. Well, now the spooler starts up. It tries to write to that one, succeeds. Tries to write to that one, succeeds. Tries to write to that one, fails. Okay. Actually, the despooler would just stop, and it would stop for all markets. And 2 minutes later, it would try again, and it would stop for all markets, and so on. So none of the markets would proceed, which actually violates our principle, right? Well, it turns out to be like 20 lines of code where we would implement a circuit breaker for the particular market. So you'd say, I failed to write to market 6. Just make a note of that, and anytime we come up with samples that need to go to market 6, ignore them for now, but we can proceed on all the other markets. A very simple change, and it solves the problem. Okay, what about servers filling up? I don't want to show you that yet. Ideas, servers filling up, right? We can make the servers bigger, but there's a big problem with that, which is even though indexes are supposed to give you logarithmic behavior, that accessing data should take logarithmically longer as the data grows linearly, in certain cases, MySQL really doesn't behave that way. So if I want to get 1 day's worth of data, and it's the same number of samples every day, regardless, 1 day's worth of data out of a month's worth of data, it takes a lot less time sometimes than getting 1 day's worth of data out of 2 years' worth of data. And it shouldn't be that way, but there are certain things that MySQL fails to optimize, and they simply don't. And in fact, in our V2 design, we had to work around that issue. So just making the databases bigger exacerbates that problem. So one solution that really is pretty new is database partitioning. Let's say we create a separate table for each month of data. Then all we have to do is drop a table. Drop the table that's 3 or 4 months old. That'd probably work pretty well. We don't have that solution. The solution I came to, whoops. I'm not going anywhere. Oh, I'm on the wrong screen. It's scrolling over here. Okay, application level, yeah. Okay, the solution is you don't put all 3 servers in play at once. You put servers in play every month or 2. So what happens is this really old server is kind of full. And for me, full is not 1.5 terabytes. Full is maybe half of that. I don't ever want to go more than half of the space on a server. And you can do the math, and maybe it's not going to work out that way, and maybe we need to go with 750 gigabyte drives or something. But when the server fills, we retire it. But we don't retire it until we put a new server in place. So we always have 3 copies of the data, right? And if we're going to retire the server, we might stop writing to it, but we don't erase it for a month or whatever it is because of our policy to keep 3 copies of the data. But that's okay. Once we actually honestly don't need it because of our requirements, the 2 to 3 months, we can reformat it and use it as a newest server down the road. Now, what's great about this is there's no possibility of creeping corruption. How there's maybe something wrong, and maybe it's not MySQL's tables, but maybe the file system is doing something funny. And sure, my ISAML or FSCK will fix that, but who can do that on 1.5 terabytes anyway? So, and if you get to where you have to do that, that's not so cool. You've got newly formatted disks coming into play every month or 2, and it solves that problem. Now, what's another nice thing about that is this hardware works. So when you put it up at the top, you don't have to worry about is this going to have DOA problems. You buy something new and it's going to fail surprisingly often. So this was the solution that we designed in, but they didn't implement it. They just let the disk fill up. So that's, yeah.
So, one thing with this is that you're not quite doing it at the application level, you're doing it at the output.
Yes, but this is new servers that, remember I said we want to work with an installation that's essentially as close to a Debian install as you can get, or an Ubuntu install. All you have to do is build a new server. And maybe apt-get install MySQL or something. This is not going to require any configuration of replication and so on, right? Now, when I say it's strictly not strictly true that you can just do a straight-up install. That would work pretty well, but there are certain really subtle performance things that you have to worry about, which, I don't know, how are we doing on time? Okay, and how long are we supposed to go? Because we're getting close to the end. So let's just, sorry?
8:30 or 9, I think.
Oh, okay, okay. So it is an ops issue. You've got to have ops. I'm not saying we don't need ops, but I want to minimize what they do. Makes it a lot easier to find people that know how to install Ubuntu than know how to do replication your particular way, and not only that, but make sure to recover from things the right way. Remember, for example, I didn't talk about it explicitly, but if, let's say this server goes down, okay, and the despooler trips the circuit breaker for that particular market, so that market is not despooling. And Nagios sends a page to the administrator, and one of the things they can do is they can come in and try to reboot that server, fix that server, whatever. But if that's going to take them more than a few minutes of time, they can simply update the map table we talked about and take that server out of the loop. So now there's only 2 servers in that market. And then you run mirror, and it broadcasts it everywhere with a single command. And now everything is back up, and that market is despooling again. And then they can take their time, and it takes them a few hours to fix this server. Or let's say maybe one of the hard drives failed, and since it's RAID 5, the server is still in play, but you want to take it out of the loop, and you do the same thing. You fix that hard drive, and now you want to put it back in play, so you simply put it back in play by updating the map table, running mirror, and now the despooler is despooling to it again. And the only problem is there's a little hole in the data, right? Well, we have another command that isn't as generic as mirror. Mirror is has no knowledge of the application. We have another command that has some domain-specific knowledge, but it can go in and simply fill the hole. And it can just do that. And it might take a half an hour or an hour or 2 hours, but it doesn't matter because it just happens. We don't have to worry about all of these things that have to happen in the right order if we're dealing with replication. And when I say they let the servers fill up, well, really what they do is they let the servers go as far as they can in that terabyte and a half. And then obviously it's time to get new servers in there, so they'll put new servers in, and then they'll copy some of the data onto the other server, not all of it, using the same kinds of tools, the hole filling tool I talked about. And but let me point out, they can put the new server into play before they do that. And that's it. So it's not as simple as this scheme, and the tables get a lot bigger, and so performance suffers a little bit, but it's still pretty flexible. Okay, the results. So yeah, I implemented this pretty much by myself in the first 4 months of last year, and I wasn't working full time. I mean, I wasn't working full time for them, but I also had other responsibilities working for them. So it really wasn't too hard to implement. It's been running well since then, and it works well. Turns out they want to keep all the data. You know, the design requirement, I ran this up the flagpole several times, and it's in documents, signed off, 2 or 3 months worth of data. Well, we keep it all. So now that's a problem, right? And I don't think they're keeping all of it now, because now it's more than will fit. So it also turns out they need to do reprocessing quite a bit. And this has not to do with the samples coming from the phones, but it has to do with the samples coming from the media monitors. We have to know when certain ads ran on certain television stations. There was that third category of data that has ads in it. And we do acoustic matching, we can tell when the ads ran on the data. And the problem is the ads come in late. You know, we want the ads before they're aired, and that doesn't happen. But what's worse is they want to know what happened six or 8 months ago. So we have to go and reprocess a tremendous amount of computation. And this is these compute nodes doing acoustic matching, but they pound the database servers because they have a lot of data to get off the database servers to do the acoustic matching. So basically, they're running the system at 30 times. Well, let's put it a different way. The system runs at 30 times the performance it was designed to run at, right? I never figured out how fast it would run. I just tested to make sure each component would be fast enough. And so clearly, even though we're doing application level replication and all these things, there's plenty of extra capacity here. And with it running at 30x the design performance, they then complain that the database servers are running too slow. Right? They don't get the instantaneous response even though they're hammering these things. So what to do about that, I don't know. I guess we should change the design requirements and give this thing a... But if you did that and made it run at the 30x as a design requirement with some overhead, then they try to run it at 100x, typical. So it's an interesting question. We've had an unbelievable number of server failures. Hard drives, we've had 30 or 40 hard drive failures. And I don't know what's going on. Somebody who was here last time suggested that if you tighten the screws too much when you put them into the chassis, and then you put those chassis in the rack, you can get these resonances in the rack. I don't know, but we shouldn't be getting 30 hard drives failing. And despite that, data integrity has been maintained. There's been a lot of having to fill holes in things.
Whose hard drives are used?
I don't know. That's somebody else's problem. And they're the ones who decided they had to spend a lot more money. So it's working well in Nielsen and IMMI. Based on the data coming out of this V2 system, IMMI closed the deal with Nielsen. And it's been in the press that IMMI will be providing out-of-home viewing data for Nielsen's customers, which would be the networks and whatever. Now, it's not related to the topic, but how do you know if it's out-of-home viewing? Something we didn't talk about, right? Because we're doing the acoustic matching, but we don't know where you are. And a cool solution would be if you could use GPS on the phone, right? But that's impossible to get from the carriers these days. So what we do is we put Bluetooth beacons in their homes. So phones have Bluetooth turned on, and one of the data that's coming up in addition to the samples, there's a whole bunch of extra data, is a list of all the Bluetooth beacons that you see. And so then if we recognize some of them, we say, we know that's in his house, so he must be at home. And otherwise, we know he's out of home. And what's really cool is we did a particular project for the Super Bowl. And we found that something like 53% of Super Bowl viewing was out of home. And this is statistically significant data that we got from our panels. Now, here's the great part is currently, if a Nielsen panelist views television out of home, that viewing doesn't get counted, which means that Nielsen underreported Super Bowl viewing by more than a factor of 2. And we know that statistically significantly. So, lessons learned. Unless you're in charge, and I wasn't in charge, you probably want to stick to conventional wisdom, such as do it with replication, don't use blobs in databases, don't use Perl. That's been a huge issue. You'd be crazy to run a database on RAID 5. You have to use RAID 10 for that. And all these changes are being made. Software and hardware, now that's politics. In terms of actual technology, software and hardware never perform as expected. And I didn't talk about these things. I've talked about them before in this meeting. There's a MySQL join issue, where if you join two tables and you have a where constraint, where one of the columns is on one side of the join and the other column is on the other side of the join, MySQL simply can't optimize that. And you get these horrible degenerate issues. So for example, if I want to pull 1 hour worth of data for a panelist, and remember I have that the map table, or the panelist management table tells me how to find the panelist, and then I also have the metadata for the samples has dates in it. So if I say, give me panelist 37 for this 1 hour time frame, that happens instantaneously. If I say, give it to me for 2 hours, it takes about twice as long. And what that translates to is there's time for it to get the data off the disk. It's reading the actual data, not going through the indexes. That takes twice as long. It's just the disk I/O time. If I say, give me 3 hours, it takes 3 times as long. If I say, give me 4 hours, it takes 100 times as long. And I did this as an issue with MySQL AB, and we went into it, and they said, oh yeah, it can't handle that, and it won't handle that. That was.
What's the scenario again?
The scenario is I'm joining two tables, and I have a where constraint. It's indexed and all. I have a where constraint where the where constrains one column here and one column here on opposite sides of the join.
I think that the problem may be, when you pull more data into the box in the RAM, and it doesn't have enough memory or swap or something.
Yes, all right, but it's clear if you think about it that this problem could be solved in a very low memory footprint. And I think you're right. What's happening is the only way it knows how to solve it is to use a huge amount of memory, even though it shouldn't need it. And so it was frustrating. And in fact, we ran into that with V1. And what's worse about it, what's insidious about it is you don't run into that problem until after your system is up and running and performing beautifully for several months. And then all of a sudden it hits this wall. It goes from, taking the expected amount of time to this big jump. And all of a sudden your system stops working. And in fact, I ran into this problem at a previous startup, that one, Colloquis, back in like 2000, 2001. And we didn't identify what the problem was then. We stopped using MySQL. We ran into it again in 2005, and I said, this smells familiar. And that's when I went out and came up with a test case that demonstrates it. So when we did V2, I simply worked around the problem. And the solution is, forget about normalizing data, especially with what I was doing is like a data flow kind of an architecture. You want your databases to be normalized if you're doing transaction processing, and if they change their name, you got to have you don't want them you want that to be reflected on all the invoices, for example. But in our case, as we're doing acoustic matching, I take the panelist ID and I put it in with the metadata on the other side. I don't keep it factored, and it's no big deal because the data is flowing through, and solves the problem. Because we're not doing a join anymore. We just get rid of the join by essentially pre-joining the data as we do the computing. We denormalize, yeah. Okay, RAID 5 ext3 just doesn't work. So I'm running a benchmark with MySQL on ext3 on RAID 5, and what you get is, every 10,000 records, tick, 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 tick. Nothing, nothing, nothing. Tick, 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 tick. Nothing, 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 nothing. You try to figure out what's going on here. And we went every which way. Okay, so it has something to do with the journal. Well, clearly, because ext2 doesn't show the problem. So maybe it's because it's writing, updating the journal. Writing, updating the journal. So we even went so far as to, ext3 has the ability to tell you to put the journal on a different device. So we had our data disk, and we had a separate disk where we put the journal. The problem didn't go away. So I actually put the journal in a RAM disk, which of course makes no sense, because if you lose power, you lose your journal. And the problem didn't go away. But turning off the journal fixes the problem. So the answer is, don't use RAID 5 with ext3. We switched to either XFS or RiserFS, and the problem went away. And then writing was tick, tick, tick. And the data rate for writing data into MySQL was phenomenally high, which is the benchmark I did to determine that I could despool fast enough on a single spooler, and that impacted the architecture down the road. However, we chose Riser, and it turns out that Riser has a rename problem, apparently. We use rename for a lot of things. So we have the spooler writes the data to the disk, okay, and at that point, you want another process to despool, okay, and so we did what we call chaining, directory chaining. And so what we did is you take that one file and you rename it into another directory, and that's atomic under Linux. So it has all the right properties. That if two processes try to do it, one will succeed, one will fail, and so on. And that way we could keep track of exactly whether a file had been, you don't want to read it and write it and erase it and stuff, because there are windows in there where the file doesn't exist on disk or exists twice on disk. And if your process craps out, you can end up with issues. So rename is perfect, except we did a lot of renames, and Riser kept corrupting the file system. Now, XFS would be another good solution, because we like the idea of a journal, since we have 1.5 terabytes of data on this thing. But I believe they just switched to ext2, and all the issues in that way went away. If they have power failures, they might run into trouble. Shazam melts the servers. I mentioned that already. And in fact, in order to get the Shazam to the optimal performance, I had to run 7 threads at a time, 7 processes actually. And I just tested it, and more didn't speed up, and fewer it slowed down. And see, now I'm thinking I should have just backed off to 6 or 5, and I probably would have stopped melting the servers. But that's the point is, servers don't melt. You go to design a system like this and put it together, and you expect that kind of thing to work, and it doesn't. So when you do a big architecture like this and start building it, don't have assumptions. You've got to test all the things, and nothing is as advertised. And then I mentioned already, requirements change. So over-design, as they'll expect you to do it to do more than they asked you to build it to do. And overbuild, I mean, one thing is, if you do have downtime, so you know, if you calculate the size of the problem and you say, I need this much, say, processors to do acoustic processing, that's cool if you're always running steady state. But let's say everything goes down for a day. So now you have to do twice as much work. You need twice as many processors because you need to not only keep crunching on the new data coming in, but you need to catch up. And you want to catch up quickly. So in fact, we over-designed by a factor of 3, which is why we were able to do 30x over the design. And where the factor of 10 came in is simply that everything's a lot faster than it needed to be. I think that's all I have. Great. So I can do questions. If you're interested in other elements, this is all getting posted to Google Video. And some of those things I definitely don't want to talk about on tape. But whatever. Yeah.
Question, when you say Shazam melts the servers, you mean...
Not physically, but almost. We had bunches of different kinds of, well, there were really like 2 or 3 different failures that we saw. And my latest belief, and remember, nobody actually got to the bottom of it. And I really wanted to, but I was one guy doing all this stuff. I believe we had that issue with Riser, with rename, and we also had an overheating problem. And because, and I mean, how many people really have experience with running code that makes the processor run hotter? You know, this is not something people run into day to day. And, you know, do you even believe it? Show of hands, how many people believe it happens? Or don't believe it happens? You don't believe it happens.
If you've got machines sitting in a data center somewhere, it's kind of hard to tell what's happening.
Well, these were sitting, you know, in our back office, and we had a cool room. We knew it happens, and, you know, you can read the spec sheets, but we didn't realize how much it happens. So we actually put thermometers in there, and we measure the current. And it's tremendous, the difference. These new processors are designed very efficiently, especially the EE processors from AMD, for example. And the swing in power usage can be a factor of 2. And, of course, that translates directly into more heat. And so it definitely dumped a lot more heat into these were one-use servers. And so that had several effects. First, we had a riser file system issue. And secondly, we had this really hot chassis, which was overheating the hard drives as well. And I know it actually, when I say melted, it's because these servers, once they failed, just letting them cool off and turning them on again, they were never the same. They would fail more and more often and this kind of thing. So they somehow could remember that they had these problems. And this was a big issue.
That was just CPU intensive kind of stuff?
Oh, it's totally floating point intensive. I mean, Avery Wang is the guy who invented the technology at Shazam. He now works for IMMI, by the way. He loves to explain to you why this sequence of assembly language instructions is better because the translation look-aside buffer designed into this CPU is, you know, and so this thing is full out doing acoustic matching, and his stuff is extremely fast. We can go through 1,000 hours of audio and do an acoustic match against a single sample. We can do that at the rate of about 30 per second. Now, I don't know that doesn't mean anything, but I mean, it's doing a lot very quickly. And the CPUs are pegged when you do this, and it's a dual core, and it was to the point where we'd buy these new expensive servers would come in, and my colleague Derek Wolverton, who was in charge of the acoustic processing, he would just go and fire up these tasks on those particular processors and watch them melt. I mean, you know, a certain percentage of them would simply fail pretty quickly, and then others would fail over time. So it's a problem that we didn't really resolve. And hopefully maybe the blade servers are better, But otherwise, I would simply scale back the computation and buy more servers. Other questions? Yeah.
Just out of curiosity, what's the data path to upload from the cell phones to the school?
Yeah, we use the wireless web. So basically, we have software running on the phones that turns on the microphone and records. And then it does, in this particular implementation, it does the spectral fingerprint, the Shazam fingerprint on the phone, which significantly reduces the size of the data to about 4 kilobytes. And then it just does a HTTP post to our web servers right from the phone.
Okay, that doesn't interfere with the use of regular use of the phone?
Currently, when you answer the phone, we stop sampling. And the reason that's designed in is a privacy issue more than anything else. Even though we're only getting spectral fingerprints, so you can't listen to these things anyway. But I suppose it's possible that you're talking to somebody and they're listening to something in the background. We could pick that up. This stuff is tremendously sensitive, by the way. My cell phone, that 3125, I used to carry around in my back pocket here, and it would catch the television just fine. And then I go out and get in the car, and I'm sitting on it, right? And it would pick up KQED flawlessly. It was much better than we expected in terms of sensitivity.
That's just using the regular microphone in the phone?
Yeah, yeah. So, and we're using just a regular wireless data. However, as I said, there's a lot of gotchas in all these things. One phone, for example, was not able to sample from the microphone and transmit at the same time. For no good reason. But we had to work around that. Not one phone, one particular model. Yeah. Questions?
So just comment back on melting the servers.
Yeah.
I remember someone at Google actually talking about when they did stuff and they were building servers doing a lot of computation. They just simply didn't put the chassis in place. They just put the...
Yeah, their original design. And
yeah.
you can still see that in their lobby, their main lobby.
Yeah.
And all the boards are sagged and there's wires everywhere. Yeah.
But you just get, the amount of cooling that you get with that is just...
Well, but see, Google did a lot of funny things. When I did that Colloquist company started in 2000, and I went to pick my cage at Exodus, and this was in 2000. And I picked this cage, and right across the hall was these really nice looking racks. And I said, oh, those look really nice. I want to see what the back looks like. And go look at the back, and it looks exactly the same. And it was rackable equipment, which they take the standard, well, they take racks that are a little bit wider, and they put servers, short 14-inch servers, they put them in both sides. So they're drawing air in like this, right against each other. But then they put a big fan on top and get this convective updraft. And so they get twice the density of servers and can cool them better than anything else. So when Google built those servers, they were very cheap about the power supplies they built. And they didn't put any power factor correction. They didn't buy power supplies with power factor correction. And so they were driving like 50 amp imbalances through Exodus. And so we had to worry about this because we were on the same power conditioner and stuff. And it was really funny. So they have all kinds of extra issues to worry about. I mean, they're really exceptional. They do integer stuff. Maybe that doesn't melt the processors as much. Who knows? Yeah. And it was a real problem. And buying really expensive stuff. We bought off-the-shelf Opteron, dual-core Opteron servers that other businesses that my other company bought that worked just fine for our application, and we would melt them every time. So it was surprising.
How do you use the data? You said that when you retire the service, you actually, after like 3 months, you delete all those data, or you ever do summary information out of those data?
So what I talked about here was called the data pump, which the goal is to implement the core of the technology, the phones and the media monitors and so on. And what comes out is simply the raw channel impressions. Panelist number so-and-so saw ABC in Los Angeles between 11:15 and 11:32. And that's it. Okay. Now, that data then goes into a whole other process for generating reports. And I didn't talk about that at all, and that's actually, different customers need different things. So it can get complicated, but it's not the core technology. And you could imagine that lots of companies could take the data as I've described, the results of the data pump, and make use of it. For example, Nielsen doesn't need all of our reporting infrastructure to make use of the data. And companies like Arbitron are perfectly used to the lower level data as well. But then there are other kinds of companies who aren't used to that level, and so we can do all kinds of different reports for them. Okay. Is it a wrap? Yeah, more. Okay.
So back to another thing that you had mentioned earlier, comment about not having a date field in your table.
Yeah.
Being able to do deletes in there. One way I found to go deal with the problem after the fact, when you've got lots of code written that already knows about the table and everything like that, is you go add something which is a timestamp instead of and a timestamp field will automatically put in the time value.
But consider this.
Change on the front end code which is doing the write there.
But consider this, right? That they let these tables fill up much more than I ever expected. Notably, one table was bigger than that half of that terabyte and a half, right? And if you go to add a column in MySQL, what's it going to do? It's going to rewrite the whole table.
Well, you just put it on your new server.
Well, yeah. So there's lots of ways we could do that.
Kind of flow back in, after a couple of months.
Yeah. So certainly, when we deploy new servers, we could simply have done that. Yeah. Yeah. But at that point, it wasn't really my concern anymore. So I'm on to my new thing. My new thing is, you want to hear about that for a moment? How many people have smartphones? Like Windows Mobile, Palm, Symbian? Okay. So what it is it's software that helps you get access to web content much more quickly than you can simply through the browser. And the way we do that is we have a custom app that you download to these different platforms. And it has a bunch of different channels. So for example, you can pick the Wikipedia channel. And then you can type characters that would be characters that occur in the article name. And with each character that you type, it's doing a round-trip query to our server. So for example, if you want to look up Richard Milhouse Nixon, you could type RI space M space N, and it would be, you'd see this list of, you start with a list of all Wikipedia articles. It's like 8 million long because it includes cross-references. And it would go, and then maybe number 3 would be Richard Milhouse Nixon, and you can go select it, and you're there. So we have, but what's really interesting about the software is that new channels can be deployed purely server-side. So the clients on the phones are generic, in the same way that a web browser is generic, and you change the application by changing server-side. So I recently created a Facebook channel, for example, which is a front end. You can think of it as a front end to Facebook Mobile, and it makes it much more usable. If I wanted to hook up with you guys on Facebook, I could type in the first few letters of your first and last name, and we get this list, which would, oh, there I am, and I just scroll down to it and say menu, add as friend, and we're done. So that's what the software is all about. It does flight status. Real-time flight status. You can type in SJC space SNA, and the list is going and there's all the flights from San Jose to Orange County, like that. So if you want, that's called boopsy.com. And if you have phones, it even runs with Java. Like pretty much any Sprint phone will run the software. All right, anything else? We could call it a wrap.
Yeah, thank you.
Good. Hey, thank you.
Yeah.